Okay, welcome to the February FPGA seminar, and we have Mohamed giving an extended version of his award-winning best paper, FPGA.
Thank you, Paul, for the introduction, and thank you all for coming today. I'll be presenting the case for embedded networks on chip for FPGAs. If I can get this to work. Yeah. Okay. So first I'll motivate why we're looking at networks on chip for FPGA, and then I'll present two variants of the embedded NoCs that we've come up with. Then briefly I'll go over a high-level summary of the area and power analysis that we did. And finally I'll compare embedded networks on chip against point-to-point links and buses that are configured out of the FPGA. Okay, so here's a schematic of an FPGA. We have logic blocks, we have switch blocks, and we have wires. Generally, the switch blocks and the wires are the interconnect of the FPGA. Of course, this picture is very outdated because now we have hard blocks, and these implement widely used functions very efficiently, such as memories, multipliers, and even complete processor cores in current chips. More importantly, perhaps, we have these hard interfaces, such as DDR controllers and PCI Express transceivers, and they're very important for the commercial success of FPGAs. Now, the first thing that you'll realize is that the interconnect is still the same. We're still using switches and relatively short wire segments to connect everything together. So even though we raise the level of abstraction of the logic through these hard blocks, and the level of abstraction of the I/O through these dedicated hard interfaces, we're still using the same low-level interconnect to connect all of this together. And this is starting to pose a few challenges. Now, for starters, there's a speed difference. For example, hard interfaces, if we take DDR3, for example, running at 800 megahertz, that's double data rate, so that's 1600 megabits per second, so that's 1600 megahertz. Hard blocks, in some cases, can run as fast as 800 megahertz, while if we create a system-level interconnect out of our current, soft logic and soft interconnect, we'll only reach about 200 megahertz if we're lucky. So this is sort of the first problem. I'll start to list the problems with the current interconnect here. So the first thing is this bandwidth issue. We're getting a lot of bandwidth from these I/O interfaces, and we have to process it or distribute it around the whole chip using this relatively slower interconnect. And this is becoming difficult. It's also very difficult to close timing on those hard interfaces especially. That means meeting the timing constraints of these I/O interfaces. In fact, the only way to do it is to go parallel. So in the case of DDR again, it runs at 1600 megabits, right? And it exposes 64 pins to the FPGA, but we have to parallelize that almost 8 ways to a 512-bit wide bus, and we must carry that bus over the entire chip if we want to transport that data. So that's kind of a challenge. So it's a huge gap problem. It chews up a lot of the power and area available to us on the FPGA, and it causes slow compilation among other things. The fourth problem is a more fundamental one, is that global wiring is not scaling very well as transistors. So to get a wire or a metal wire that spans the entire chip, it is not scaling as well as transistors. So delay is becoming more and more interconnect dominated, making it harder and more difficult for designers to complete designs using these wires, basically, these unstructured wires. Okay, so I like to use the analogy of a city. So here we have an old city, small buildings and narrow streets between the buildings. Now, each building block almost looks like a logic cluster, right? So because we generate only very little traffic in that city, we can process all that traffic using the narrow streets and roads between the buildings. Then when we move towards a larger city, we still have the logic blocks, we still have those small buildings, and we still have the small streets around them. So the regular interconnect that we have right now is great. But we also have these very large hard blocks that generate a lot of traffic. For example, the malls and the high-rise building and the companies. And we also have hard interfaces like airports or train stations. And we know that these generate a lot of traffic as well. So we must do something about this traffic. So we must widen the lanes and raise the speed limit and add a network of freeways to be able to process all that traffic during rush hour. So what I want to convey through this slide is that we want to keep the roads. We need the roads for our city. But we want to augment that with freeways as well. So the FPGA interconnect is great, but we think we need some kind of global embedded network of freeways to handle that extra traffic as well. In case you're wondering, this is Barcelona and this is Los Angeles. I think most of you know where we are. Okay, so that's what we want to do. We want to add a network on chip to our FPGA. And so a network on chip consists of routers and links. Routers are responsible for deciding where data, to switch data basically, and links transport that data between router nodes. So if we want to move data from this DDR block to this green block here, it will be packetized and then moved on the network. The first router hop will decide where it goes next. And then when it reaches its destination, it will be moved from that network of freeways. It will take an off ramp and go onto the regular interconnect, where it can access any block on the FPGA basically. So just like this. Now we still have the problems with the current interconnect listed here, and we'll see how we can solve them using, or mitigate some of them using the network on chip. So for the first two problems, we know where this high bandwidth is coming from. It's mainly coming from these hard I/O interfaces like DDR or PCI Express. And so we can, instead of using the unstructured general purpose interconnect to connect those interfaces, we can tailor a network on chip with the timing requirements of these I/O interfaces in mind. So we don't have to worry about timing closure using an unstructured network of short wires and fast transistors basically. We can do it in a better way by embedding a network on chip that has these requirements into it. As for high interconnect utilization, so NoC links are reusable, so we immediately make better use of the metal. And a network on chip will also not use the same number of configuration bits, so it sort of simplifies the CAD problem. We'll see it later how it can simplify the CAD problem even more. For wire speed scaling, the NoC, you can look at the NoC as a heavily pipelined network of short wires or relatively short links and router nodes. So each router node can be almost looked at as a pipeline stage. And so we already have a pre-pipelined interconnect in our system, which gets rid of those large global wires that are very slow. And sort of a bonus on top of that is that the network on chip abstracts the communication on the FPGA. And this abstraction is great for FPGAs and things like parallel compilation, for instance. So if we have 4 modules in our FPGA and they only communicate through a network on chip, then there are no critical timing paths going between them. They're timing disjoint. The network on chip provides a latency insensitive or a latency tolerant communication substrate for you. So we can basically compile them all in parallel and parallelize our compilation problem. For partial reconfiguration, we have a similar advantage because we can just swap out a module and swap in a new module, and it's instantly connected to the rest of the FPGA. We don't have to route this new module's connections in an already functioning FPGA, which is the main challenge of partial reconfiguration. And similarly for multi-chip interconnect, because we can tolerate latency in our NoC, we can sort of make the connection between chips almost transparent, whether they're chips on die or chips transposed. Okay, so we think that NoCs or embedded NoCs can simplify FPGA design. In the rest of this talk, I'll show how we think we can integrate NoCs on an FPGA, and I'll show some results quantifying whether this abstraction comes at a high area and power cost or not. The answer is no. And how embedded NoCs compare to current interconnects configured out of the FPGA fabric. So how does it compare to what we currently do? All right, so we have 2 types of NoCs. We call them mixed and hard NoCs. So this is sort of our design space here. We have a router and links. That's what makes up our NoC. We also have this fabric board that interfaces our NoC to the FPGA fabric, and we'll talk a little bit about that later. So we can implement the routers and the links either using soft logic or hard logic. Soft logic is just configuring it out of the FPGA fabric. Hard logic is where we embed a specialized block for that. So if we use soft routers and soft links, that's what we can do right now. We can create a soft NoC, and we'll use that to compare to our hard NoC. If we use hard routers, so we're embedding the routers, but we're still using the soft interconnect of the FPGA, that's an interesting design point, and we call it a mixed NOC. If we embed both, so we use hard routers and we use dedicated metal wires between routers, then we call that a hard NOC. So very quickly, our methodology. For anything that is soft, it goes through the FPGA CAD tools and compute area and speed. For anything that is hard, it goes through the ASIC CAD tools. So we're assuming an ASIC design methodology, not full custom design or anything else. And that's Synopsys Design Compiler, and we design the hard wires using HSPICE. And then we do a gate level simulation to find bandwidth numbers, and also to compute toggle rates, which are used to accurately model power. So anything that is mixed, it takes results from both design flows. Okay, so first the mixed NOC. Here is part of an FPGA, so we have logic blocks, and it's surrounded by this programmable interconnect that we have right now. Now mixed NOCs have hard routers, right? So when we embedded one of those hard routers with these baseline parameters, it took the area equivalent to 9 logic blocks. So we removed 9 logic blocks from the FPGA, and we put a hard router instead with these parameters. And remember, we're still using the soft interconnect to connect that router. So at the router interconnect interface here, we use the same kind of programmable multiplexing to access sort of our network of programmable interconnect. That means 2 levels of muxing on each input and 1 level of muxing on each output. And we account for that area and power in most of our results as well. So of course we have many of those routers in our FPGA. And a special feature here is that we can configure the topology because we have control over the links, basically. So I'm showing a mesh topology here, but we can also use a subset of the routers to create a ring topology. We can create 2 NOCs, for example, those butterfly networks, which may be suitable for talking to DDR, for example. And we can just do that by reprogramming the routing tables or the routing units in our NOC routers. We can also do a fully custom topology. So this kind of programmability is, it goes well with the programmability of FPGAs, right? It provides a lot of flexibility. When we go to hard NOCs, we still have the hard router, right? But we added the dedicated hard links as well. So that's dedicated metal wires to connect one router to the next. So now we don't need multiplexers anymore. We just have wire drivers at the inputs and outputs to basically drive those wires. So we don't have the extra area or power overhead of programmable muxing. And we can connect them in a fixed topology. In this case, we chose a mesh, but we still have a special feature here. So we can't configure the topology, but we have something called low V or low voltage mode. And that's basically when we use a separate power supply for our network on chip than the actual FPGA. And we can do that because the NOC is very much disjoint from the FPGA now. It only connects through this fabric port, and we'll show that we can just add some voltage crossing logic in that fabric port. So in our case, we were prototyping this on Stratix 3 FPGAs, and we ran 0.2 volts lower on our NOC, and by doing that we traded 15% speed for 33% dynamic power. So that's hard NOCs. Now, I sort of glossed over the fabric port before. I'll gloss over it again now. I'm not giving the details yet, but it's basically a bridge between the NOC routers and the FPGA fabric. So because our network will run faster and possibly at a different voltage, we need width adaptation and frequency adaptation and voltage adaptation between those 2 things. And we could also implement some bus protocol in there so that you can just plug in your different IP and connect to the network. And then it will translate it into a simpler streaming protocol that is available in the NOC. So the fabric port is responsible for these things: width adaptation, frequency adaptation, voltage adaptation, and we can also implement a bus protocol in there so that it's embedded and it's ready to go. Okay, so that brings me to the first results part, and before that, I'll just say which router I'm using. So the router architecture I'm using is from Stanford. It's a high-performance packet switch virtual channel router. And so the NOC community have sort of excelled at building routers, so we just use what they have. And we configure it so that it's a high performance variant of that router that has virtual channels and other things. And that is to meet the high performance requirements of the FPGA. And also because things like virtual channels can be used in assigning things like traffic priorities, which may be useful for FPGA designs. So we sort of use a high performance, full featured router in our experiments. Okay, so this was sort of our previous work. High-level summary is for routers, when we compare a hard router versus a soft router, so remember a soft router is what we can build right now. It is 30 times smaller, 6 times faster, and 14 times lower power. This makes sense because we're embedding it in non-configurable logic versus basically constructing it out of lookup tables. Right? For links, the answer was not as decisive. So hard links versus soft links, the difference here mainly is because of these multiplexers. It was 9 times smaller, 2.4 times faster, and 1.4 times lower power. So we still gain something by embedding those links. We're using hard links, but it's not as compelling as hard routers. That's sort of why we have both mixed and hard NOCs. Okay, so to put these numbers in perspective, let's take a 64-node NOC on a Stratix 3 device, on the largest Stratix 3 device. For a soft NOC, it takes 12,500 logic blocks, while for a mixed NOC, that's exactly 576. For a hard NOC, that's 448 logic blocks. So that's 33% of the FPGA for a soft network versus 1.5% approximately of the FPGA core area. So that's a big difference. In terms of speed, there was a similar gap as well, so it's almost 5 times faster. Instead of 166 megahertz, we can run an embedded network at 700 to 950 megahertz. And there's a proportional increase in bandwidth, of course. So we have a 64-node network on Stratix 3. It provides about 50 gigabytes per second bisection bandwidth, and it costs less than 3 soft routers, basically. So if you have a design that wants to use a network on chip and it has more than 3 things that want, or 3 routers in the design, then you're better off using a full-fledged 64-node NOC, which is composed out of hard logic. So it's very cheap. So we sort of quantified the area gap in the previous work, and we wanted to do a similar thing for power now, because power is a big concern. So what we did here is we estimated the power budget that we have on the FPGA by modeling an almost full FPGA device of the largest Stratix 3 device, and with reasonable toggle rates and with reasonable utilization of the logic. And when we measured the power, it was almost 17.5 watts of dynamic power. So that's sort of the power that we have available in our FPGA. That's our maximum power that we can do. So we wanted to answer the question of how much of this is actually used for system-level communication using something like a network on chip. So we say, okay, we'll construct an NOC that provides 250 megabytes per second total bandwidth, and we'll see how much of that pie, basically, each one of those variants takes. So for soft NOCs, it was more than the available power that we had, and that makes sense because it doesn't even fit on an FPGA. A network on chip that's composed out of soft logic, at least for our routers, that provides 250 gigabytes per second is not even feasible. For mixed NOCs, it was much more promising because it only takes 15% of our power budget, of our dynamic power budget, to move that amount of data around the chip. And by the way, that's not like a theoretical maximum of what the network can provide. We simulated it using model sim under worst case traffic conditions. So this number is conservative, somewhat conservative. For hard NOCs, we got 11% because we're saving a lot of power at the links as well. And when we did this low voltage optimization that I talked about, it was even lower, as you would expect, at 7% of the FPGA. So that's 7% for 250 gigabytes per second of bandwidth moving around the chip. So I've been saying 250 gigabytes per second, but let me put that number in perspective. So assume that we have the entire bandwidth of DDR being transported across the chip to module 1, the entire bandwidth of PCI Express Gen 3 being transported across the chip to the other side to module 2. So that full theoretical bandwidth is annotated here. So the aggregate bandwidth computed by adding all those numbers together, basically. And what we get here is 126 gigabytes per second. So that's half of what I reported for before. So our most efficient NOC would use 3.5% of the dynamic power budget that we have available to move that bandwidth on the NOC. Okay, so on to the last part, and I think this is the most interesting part. We will compare our embedded NOC against point-to-point links, so just wires basically, and buses that are used for system-level communication, composed out of the Volterra's system integration tool called QSYS. Okay, so just a quick recap on the kinds of FPGA interconnect that we have. So we can construct interconnect out of just wires. We can just use wires to create point-to-point links. Or we can use just wires to create broadcast networks, right? We can also use wires and logic to do some kind of arbitration. And in that case, we can have multiple masters talking to a single slave, or multiple masters to multiple slaves. So this kind of interconnect requires both wires and logic. And we can have the NOC, which is what we've been talking about. And the NOC can sort of implement both kinds of communication. We can do point-to-point communication here, or we can have arbitration through the routers. Sort of, it's more distributed arbitration, but it's the same result. So in this first comparison, we compare just wires, so the simplest form of interconnect, versus the NOC, just to sort of get a sense of the raw efficiency of the network on chip and how it fares against just point-to-point things. Okay, so that's what we're doing. We're comparing a bunch of wires here. Each one of them has the length of one NOC link, and they run at 200 megahertz, which is a reasonable frequency for system-level communication, versus a full-fledged NOC. And we try to find this raw efficiency metric that we call energy, that is called energy per data. So when we take 10,000 wires of this length, we measure the total power and the actual aggregate bandwidth that they can transport. And then when we divide those two numbers, we can get the energy per data, the energy per gigabyte moved on this kind of interconnect. In this case, it's 4.7 millijoules per gigabyte. So first, we do the same computation basically for a soft network on chip. And as you'd expect, that's very high, 95 millijoules per gigabyte. So it provides very little bandwidth, 54 gigabytes per second. And the total power is quite high. But then the interesting stuff is when we look at mixed NOCs. So a mixed NOC that has these same parameters. So it runs at the FPGA's nominal voltage, 1.1 volt. It has width of 32 bits, 2 virtual channels, and 5 buffer depth in each router. It consumes total power of 2.5 watts, so that's half what the NOC, what the soft NOC can provide. And the aggregate bandwidth is now almost 5 times higher. So the energy per data is 10.4 millijoules per gigabyte. So now we're getting closer to regular interconnect, right? For hard NOCs, it was more efficient. So it used a little bit more power, but it ran faster, so it provided more aggregate bandwidth. And the energy per data is now 8.7 millijoules per gigabyte. Now comes this power optimization that we're talking about. So that's when we use a lower voltage supply for the hard NOC. And in this case, we lowered our power, but didn't really lower our bandwidth, and I can talk about that at the end as well. And the energy per data is now 5.8 millijoules per gigabyte, which is coming pretty close to this sort of fundamental kind of communication that we can construct out of the FPGA. So we try to optimize it a bit more. So we use 1 virtual channel instead of 2. So that lowers our bandwidth because we have less virtual channels, but it also lowers our power more than it lowers the bandwidth. So the energy per data goes down to 5.1 millijoules per gigabyte. And finally, we doubled the width, and that doubled our bandwidth, but did not double our power. So we're down to 4.5 millijoules per gigabyte, which is actually lower than what the regular point-to-point links can do, even though the NOC is like full-featured, it can do any kind of communication and so on. So what I got from here is that, first of all, using less virtual channels and higher width is more energy efficient for NoCs in general. And we can construct an NoC that's composed of high performance router, like switched routers, and has almost 1% area overhead on large modern FPGAs. And it runs at around 1 gigahertz. And its power, or its raw efficiency, raw energy efficiency, is on par with the simplest kind of interconnect that we can use on the FPGA. So NoCs are, at least embedded NoCs, are area and power efficient. Okay, so now sort of a more real comparison instead of the raw efficiency comparison. So in this case, what we do is we take a DDR3 controller and we try to connect a bunch of modules to it. In this case, just traffic generators, basically. And we vary the number of modules that we have and generate the interconnect using QSys. So QSys is a system integration tool that when you say, I want to connect this number of modules to DDR, for example, and it will generate the interconnect for it. What it generates is a network of multiplexers and demultiplexers, arbiters, and pipeline registers everywhere. So, and if you have a module that's not running at exactly the quarter rate speed of DDR, then it will need an asynchronous FIFO to interface this module running at a different speed to the interconnect, right? So that's what QSys can do. What we're comparing that against is our NoC. In this case, it's a hard NoC, so hard routers and hard links. It has 16 nodes. The links are wider, so it's 128 bits wide for each link. And when we measure the speed of that one, it runs at around 910 megahertz. Okay, so at 910 megahertz and 128 bits, this NoC can actually transport the entire bandwidth of DDR on one of its links. So we'll compare those two against each other. First, I want to show the design effort that is needed to create that system in QSys. So QSys is supposed to make it a lot easier than regular RTL design, as you can imagine. But we still needed a few steps to complete design using QSys. So take a small system, so it has 3 modules, and it's located physically close to DDR, so that's an easy problem. So that's easier than when our modules are located physically far from DDR. So small system, close to DDR, and just we pushed the button and QSys told it to generate the interconnect. In that case, it didn't meet the timing the timing requirements of DDR. In this case, there were 200 megahertz at quarter rate. So, and it consumed this area of power. So we had to do some more stuff to basically complete the design using QSys. So we went in the tools, we turned on all the knobs and stuff to have the maximum tool effort and added physical synthesis. We thought this might help. And this improved our frequency to 194 megahertz, but that still fell short of the 200 megahertz target. So that wasn't good enough. It didn't affect area and power. Then we added, like in QSys, you can turn on pipelining at different parts of the interconnect. So when we turned on 1 pipeline stage, we didn't meet timing. 2 pipeline stages, we didn't meet timing. But 3 pipeline stages, we finally did. And the frequency was 227 megahertz. But notice that that also comes at a large area and power overhead compared to the original interconnect that has a bunch of multiplexers, right? So these pipeline registers cost a lot of area and power. Then we made it a bit harder for QSys by placing the modules far away, so physically far away on the other end of the chip. In that case, it was harder to meet timing, so without any pipeline registers, we only did 92 megahertz. And only after adding 4 pipeline stages in QSys did we meet the frequency of 205 megahertz, so just barely meeting the timing requirements of DDR. And if you look now, so because we're further away from memory, we needed a much larger interconnect, partly because of adding these extra pipeline registers, and partly because of it's just bigger, it spans a bigger place, bigger area of the chip. So that's almost 2 or 2.5 times bigger than that for a closed system. So we thought, why not making it a bit more difficult for QSys? So we created a large system, 9 modules, which is placed physically far away. And when we did that, even after adding the 4 pipeline stages in QSys, it didn't meet time. So we still fell short of the 200 megahertz frequency. So what we did is that we identified which part of the design is not meeting timing. We added a pipeline register there, sort of manually, and then we finally met timing. And if you compare this area and power overhead here, now it's huge, right? Because we have a very large system, a lot of pipeline registers everywhere. It's all composed out of soft logic. So what I want to convey through this slide is that this timing closure process can be simplified if we have an embedded interconnect that already has these timing requirements built into it, right? So we don't have to go through this design process, and every time we find this frequency, we're basically running a full compilation of our design, which can take up to a day or 2 or 3 days, I don't know, depending on how large the design is. So if we have this embedded NOC that we know to meet timing to these hard I/O interfaces, that could ease the design effort a lot. After that, we measured area and power. So I have 2 more slides left. So here we are varying the number of modules, like I said, and we're measuring the area in equivalent logic blocks, and also in terms of percentage of the Stratix 5 FPGA. So for the hard NOC, we're always paying for the complete area overhead because we're embedding it onto the chip, and we're not, even if we don't use it all, the area is already paid for because it's already there on the chip, which is different to what you have in soft logic. So we say, okay, our hard NOC area is always there. We're always paying for the whole thing, whether we have 1 or 60 modules. So when we measured it for QSys, the area increases linearly because we have to add these extra pipeline registers, and our interconnect gets larger with larger systems, with more modules, basically. And the crossover point is actually quite early, so the entire NOC is smaller than a bus with 3 modules, basically. And the reason for that is, like, there have been NOC versus bus comparisons before, but in this case, because we're comparing an embedded hard NOC versus a soft bus, this crossover point is quite early, and we think is quite compelling as well. But there's a bit more. So when we had a system where the modules weren't running at exactly this 200 megahertz frequency, we needed those asynchronous FIFOs at the module interfaces to be able to access our interconnect. In case of the NOC, this is already built into it through these fabric ports, so we don't have to worry about it. So when we did that in QSys and measured the area overhead, it's actually, like, it's a big difference because these FIFOs are very expensive on the FPGA. So, like a 1 module system, the NOC almost pays for itself. And note that we're not using the entire bandwidth of the NOC. As I said before, we can transport the entire bandwidth of DDR on one of those links because it's running very fast. But even though we're not using that bandwidth, we're only using about 1/8 of it. It's already less area for most systems. For power, it was a similar story. The crossover point was even earlier, and yeah, it looks like the hard NOC saves power for even the simplest systems. So that is all I had for today. First, I tried to motivate why we're studying NOCs for FPGAs, compared it to a city that needs freeways to handle traffic. The normal roads are no longer enough. We went over the mixed and hard NOCs and how they fare against soft NOCs. Then we quantified the area and power budget to approximately 1% to 1.5% and 3 to 7% for power for each 100 megabytes per second of bandwidth. And finally, when we compared against point-to-point links or buses, the raw efficiency comes very close to point-to-point links when we have a high bandwidth system. And the NOC is more efficient and lower and has lower design effort, hopefully, compared to regular interconnect. And one final thing is that we packaged most of these results. So a summer student packaged most of these results in a nice online tool. If you want to check any of the results or use it in your research or compare against any of your stuff, or just you're curious or want to play around with this tool, you can go online at this address. So you can sort of create system level, you can compute system level metrics like power budget, dissection bandwidth, area per bandwidth, stuff like that. and you can also visualize the NOC, and it's a neat tool, so go check it out if you have time. And you can also do some detailed graphical analysis. So thank you, that is all I have.
Any questions?
When you did the comparison to the 10,000 wires of the different NLCs to the 10,000 wires, what did the area numbers look like relatively?
The area numbers?
Yes.
Well, when we're measuring the area of wires, remember these are just wires, so there are no pipeline registers or anything. So we account for those multiplexers, at the inputs and outputs of logic blocks.
Okay.
And I do have results for those. I remember the most efficient area NOC was maybe 4 or 5 times larger per unit of bandwidth. But that makes sense because we're not using any pipelining. So we can go over it later as well. I have it somewhere on my
So about your router, you showed some sort of ad hoc programmable topologies with the next NRC.
Mm-hmm.
How flexible is the routing algorithm? What is the routing algorithm, first of all?
So the routing algorithm is flexible. Right now we use phased dimension ordered routing. So that's when you have XY routing, basically. Like you go in the X direction, the Y direction, but it's phased. It has 2 phases, so it goes to an intermediate node and then it goes to the final node. The choice of that was more arbitrary than not. So you can replace that routing unit by anything. It's configurable in the router RTL. And you can also use just routing tables, which decide where data goes if it reaches that router and wants to go to this destination. So I think quite basically very configurable. The only limitation is you have a fixed number of nodes, a fixed number of ports for each router.
I just follow on to that. So which of those did you actually harden for producing your results?
So for the last results, it was a hard NOC. So also which routing unit you mean?
What is when you're presenting your area and power results? Which of those choices did you end up hardening? So you did dimension order for the hard knock?
Yes.
And for the mixed?
Same thing.
I have lots of questions. First, can you go to your slide with the raw performance comparison, the 10,000 wires? I'm just curious, your beginning point at the top and your end point at the bottom, you're comparing a 10,000 regular plain old wires versus hard NOC with a 64 wire link.
Yes.
And it seems weird that the power, why would the bandwidth be, actually never mind, the bandwidth doesn't seem that much. So what are the frequencies here involved in it? Because I'm just looking at the power and the bandwidth comparison. You have 10,000 wires in one and 64 in the other. You figure the ratio would be kind of similar when you take into account number of wires times frequency. So what's going on here? And voltage, I guess.
Yes, exactly. So that's like the result after taking all that into account.
Well, maybe
the wires run at 200 megahertz.
Maybe one thing to point out is that 64 wires is the width of one NOC link, but there's more than one NOC link in that network.
Yes,
okay.
so yeah, 64 wires go in each direction between each of the routers. Remember, it's a mesh topology. So here you have 64 wires going in this direction, 64 wires going in the other.
Well, this is for an entire network. It's not just for, when I see length of one NOC link, I think just one NOC link, not the whole network.
So the wires are each length of one NOC link, because I can get very big wires and compare to them.
So it's not one segment you're comparing, it's the whole thing.
So,
all right, my next series of questions about latency. That's one thing. Even if you use latency-insensitive design, you've taken care of the problem of closing timing and basically having latency with regards to correctness and operation of your design. When you do latency-insensitive design, no matter how fast stuff runs, you will theoretically close timing. So with an NOC, your latency is now variable depending on how far apart your endpoints are, because it'll change the number of routers you go through. But also, what about the unpredictable effective latency when you have congestion? Because you're no longer you're sharing links now between multiple virtual connections. You don't have dedicated links as an FPGA. What do you think, how does all this play into, simulation? So not for correctness, it's going to work, but what about like testing for performance how do people designers work with this?
So that's a very good question. I get it a lot. So what I see now, so first of all, you can sort of get around this by assigning traffic priorities, right? You can say I have some latency tolerant transfers here. They will get traffic priority equal 1. They have their own virtual channel. Nothing else can stop them. And then you can sort of estimate an upper bound on the latency that they have through the NOC. If you have a very large system with a lot of things and not really no traffic priority really, then yes, there will be some extra latency due to congestion, and you cannot predict that except through simulation, also an upper bound or a lower bound on this latency. But yes, that's what the latency has to design entails. Right?
And for your particular configuration that you've simulated and tested, what is the absolute latency through one of your routers? Through one router, do you know, like uncongested?
So each router has 3 cycles, and so at the endpoint, the fabric port will add another 3 cycles to that.
At whose clock frequency?
So
the networks or the users? The networks. Well, 6 cycles at 900 megahertz.
So you might want to, I know you've done simulations for that DDR system of latency for the QSys system versus the NOC. So what's the answer? When you basically have your high priority, you're not blocked.
Okay. I have to remember the number again now, but it was close to what we got with QSys. So QSys, because we added like 3 pipeline stages, and on the NOC. Well, let me bring up the number. It's in that last paper. So
it was very close.
They were very close.
It was like 10.5 nanoseconds to go
across one router.
No, that was actually for the average between the near and the far. And if you did the same average of near and far for QSys, it was very close to 10.5 nanoseconds.
So that's between 2 distance configurations, close and far even?
It was comparing the QSys closed system to the NOC closed system, and then the QSys far to the NOC far, and just averaging the numbers. Basically, both were quite close.
But
because QSys had to add more pipelining at a slower frequency. The NOC has 2 to 3 pipe stages because it speculates, right? So per router, but at a much higher frequency.
In the end, it depends, though, for both systems where things end up being. So it's a little latency per distance is kind of with you.
Yeah, and they came up very close. So basically, it was around, it was close. It was something like 7 nanoseconds or 8 nanoseconds. It was far, it was about 12 or 14, but very like it was very close to a tie. Like the ratio was approximately 1, which was interesting. So. There are other interesting things that happen, like if you're not running at a frequency multiple of the DDR interface. So as Mohamed showed, when you put in those 512-bit wide asynchronous FIFOs, they chew up a lot of power and area very quickly. They also add latency. So that latency comparison I just mentioned to you was at a multiple of DDR, which is more favorable to QSys. Because the NOC, hardened NOC, the fabric port does the asynchronous FIFO at a high clock frequency.
And narrower too as a result, so it takes up less area.
Yeah, it's narrower, hardened, takes less area and power, because it has done before the width adaptation. We should really think about that. It's done before, I forget. Anyway, it's definitely, I forget whether we do it before or after the width adaptation, because we had to look at what was most favorable for clocking.
Before is more favorable.
Okay, so it's before, so it's also narrow. But because it's done fast, it actually, in that case, you start winning in latency versus the QSys system. Because you need a few clock cycles to do all the handshaking, basically. But now the fast clock cycles, they're all multiplied out by a factor of 4 approximately.
Because you're running at a higher clock speed, I'm actually curious what proportion of power comes from clock power?
Clock power. So we estimated clock power, and it's included in the numbers there. It wasn't much. So we have basically 64 nodes on the FPGA, so it's a relatively simple clock tree when you compare it to FPGA clock trees. And I think it was close to 5%, something like that.
So I guess
Okay.
the router is idling, waiting for information, and it's basically just consuming clock power, it doesn't consume much of it.
Yes. Oh, that's another graph of that. Yes.
Just a question, I guess. I was just wondering, I mean, you made a compelling case for NOCs, but NOCs have been around for like 10 years, I think, if not more. Have you had any feedback from, I guess in your case, Altera, why NOCs haven't made it to FPGAs,
Well-
or if they're planning to include it in the near future?
Well, I had feedback from both Xilinx and Altera, and I can quote some things from the Xilinx people. They basically said, we have a lot of people working on a lot of things, and this is like a huge undertaking. They have, I hope this is not recorded. They have,
I think it is recorded.
they currently have chips, which are their cash cows, basically. I think that was the word he used. And there is no reason to change them as long as they're working.
Right.
And something like this will need a lot of work.
Right.
I remember him telling me basically that if I come up with, you know, the IP and design methodology and everything, then at that point they may consider it, but they don't need to look at that kind of thing except maybe further down the road. But they're definitely interested in it.
So, but not anytime soon, I guess.
Oh, we'll see. Things are moving fast.
Well, we've had a lot of interest from Altera too, but yeah, it's exactly as Mohamed says, it's a radical change.
Right.
You need to figure out the CAD system, everything. So I think it's a good case for academic research. If you do something relatively incremental, it can be a challenge to basically stay ahead of the vendors. This is radical enough that they're very, well, all the FPGA vendors we've talked to have been very interested, but they'd also like us to solve lots of problems, like build the CAD system and everything, so, which is fair.
And they also worry very much about what Alex asked about, so this predictable latency.
Right.
I think most of their customers want predictable latency for designs, which is very important for verification and stuff like that.
You might want to talk about DDR in that.
Yes.
There's an interesting link between that and where you started with the micro benchmarks like DDR.
Yes, so you might want predictable latency for your design anyways, but you don't have predictable latency with things like DDR and PCIe anyways. They are latency tolerant by nature. They send you data when they can, basically. So we think that's a good place to start. And we showed that for systems that are just talking to DDR, even though we're not utilizing the full network, you can still save area and power. So why not just put the NOC over there and use it to talk to the DDR interfaces or the PCIe interfaces?
Right.
It still saves you area, it eases that time enclosure issue, and you don't have to worry about latency in your actual design. You're going to wait for DDR data anyways. Jeff?
Yeah, just further on that, I think you could make that case about a lot of things that happen on FPGAs. I mean, if you got multi-gigabit transceivers coming in where there's sometimes data, sometimes there isn't, there's FIFOs, there's clock domain crossings.
Yes.
The notion of deterministic latency is kind of already gone.
No, yeah, you're absolutely right. So that's where we're starting, from the interfaces instead of from the actual core designs.
Great. Let's thank the speaker one more time.